Okay, let's start the lecture. Now, in this lecture, we will now show that inner product induces a norm in a natural way with the help of Shiva's inequality, and we will find some interesting properties of such a norm, which is induced by inner product. Okay. So, what's this? Okay. So we will now show that we will now show that inner product induces a norm induces a norm on a given linear space, in a natural or in a canonical way. With the help of Shiva's inequality. With the help of Shiva's inequality. Okay. And we also discuss some interesting properties of such a norm, which is induced by inner product. Okay, such a norm means a norm induced by inner product. Inner product. Okay, so let us first state this theorem in which we discuss all these things. Okay, theorem. Let this be an inner product. Be an inner product on a linear space X, on a linear space X. Okay, now for each X, for X belongs to X, we define this number, we define this norm X, which is equal to inner product of X with X and rigid power 1 by 2. That's a positive square root of this number, because we know that this inner product of X with X is greater or equal to 0, so we can take its positive square root. The non-negative square root of the non-negative square root of the inner product X with itself X. Okay, it's a positive non-negative square root of this. Then this whole this we know that inner product of mod of X Y is lesser equal to this is lesser equal to norm X, norm Y. That's the first property of this. And this function, because we have defined for each X in X, for each X in X we have a number this, which we call the norm X, which is defined by the square root of positive non-negative square root of inner product of X with X. And we will show that this function, which maps X onto some non-negative real number, x is in x, is a norm on x. The function which this function from x to the scalar field k. So here it's a particular case because it maps every number onto non-negative real numbers. So this k contains that a set of non-negative real numbers. Okay, so you can take also this R set of positive real numbers and union 0. This is your case here. It is a subset of k. Okay, so we show that this function is a norm on x, is a norm on x. This function is a norm on x. Okay, that is norm का मतलब क्या है? That is for all x y in x and alpha in the scalar field k. We have this norm x is greater or equal to 0, norm x is equal to 0 if and only if x is equal to 0, and this property norm of x plus y, ये प्रॉपर्टीज आपको चेक करनी है. नॉर्म इज लेस और इक्वल टू नॉर्म एक्स प्लस नॉर्म वाई, or you know this norm x is the positive non-negative square root of inner product of x with x. Okay, and the last property, this is norm of alpha x is equal to mod of alpha then norm x. Also the following results hold. Also the following results hold. First one is the following: if norm of xn minus x, if this approach to 0, that means xn approach to x. Okay, and norm of yn minus y approach to 0, so that means this xn is a convergent sequence and yn is also a convergent sequence, which means that they are also bounded. Okay, because every convergent sequence is bounded. And then this holds inner product of xn with yn, this will converge to inner product of x with y. That means actually this inner product is a continuous function. Okay, second part is, so you can write here, that is this is a continuous function, is a continuous function, and second part is, it's called the parallelogram law. That's very important here in inner product spaces. Parallelogram law. And what's this? For all x y belongs to x, for all x y belongs to x, you can thought this as a Pythagoras theorem. Actually it's like that, parallelogram law. For all x y belongs to x, it's this norm of x plus y whole square plus norm of x minus y whole square is equal to twice norm x square plus norm y square. And the third statement is the linear space x is uniformly convex. Okay, the linear space x is uniformly convex. का मतलब क्या है? Is uniformly convex in the norm. in this norm, not in all the norms, in the norm जो हमने ऊपर डिफाइन किया, which is induced by inner product. Okay, that is for all epsilon positive there is some delta positive. For all epsilon positive there exists delta positive such that for all x, y in x with norm x less or equal to 1, with norm x less that means x is in the unit ball, norm y less y is also in the unit ball, and norm of x, this is all given. Okay, this is greater or equal to epsilon. This should imply now we must have this. इसको कहते हैं यूनिफॉर्म कन्वेक्स स्पेस, जिसकी ये प्रॉपर्टी, जिस नॉर्म की ये प्रॉपर्टी होगी ना, नॉर्मल लीनियर स्पेस की ये प्रॉपर्टी होगी, उस नॉर्मल लीनियर स्पेस को कहते हैं यूनिफॉर्म स्पेस. ओके, यूनिफॉर्मली कन्वेक्स स्पेस. ओके, एवरी जो भी नॉर्मल लीनियर स्पेस होता है दैट्स नॉट अ यूनिफॉर्मली कन्वेक्स स्पेस, बट इफ द नॉर्म इज इंड्यूस्ड बाय इनर प्रोडक्ट then that those norms have this property, the property of uniformly convex. Okay, and these are three statements, so let's prove them one by one. Proof. So first part that which you had to prove this actually it's the Shiva's inequality. You can thought of it as the Shiva's inequality. This we know that this square is less or equal to inner product of x with x and inner product of y with y for all x. आप इसको ऊपर लिखिए, for all x y. This is know that this for all x y belongs to x, this holds, which means that inner product mod of x y square is less or equal to, but this is by definition it's norm x square, because we know that norm x is the square root of inner product of x with x, so it's norm x square, and this is norm y square, right? So let's take the square root on both sides, and we get, because everything is positive here, so it is x y mod is less or equal to norm x and norm y. Okay, so norm is actually, norm x is a positive square root of this, non-negative square root of so you can cancel this square on both sides without reversing the inequality or without changing in any inequality. So इसका आपको ख्याल रखना. This is actually as you know, one is like it is less or equal to say -2 square. Okay, but you cannot cancel square here as -2 is a negative number. But here norm, actually this norm of x, what is this norm of x? It is the non-negative square root of this number. Okay, non-negative square root of this, as this is actually non-negative number, this is greater or equal to 0. इसके जो स्क्वायर रूट्स होगी ना, वो पॉजिटिव भी होगा और नेगेटिव भी होगा, बट यू चूज अ नॉन नेगेटिव स्क्वायर रूट ऑफ दिस. इट हैज टू वैल्यूज. इसकी जो स्क्वायर रूट होगी उसकी दो वैल्यूज होगी, पॉजिटिव एज वेल एज नेगेटिव, एंड यू चूज अ नॉन नेगेटिव स्क्वायर रूट, नॉट नेगेटिव. नेगेटिव आप चूज नहीं करोगे, यू चूज नॉन नेगेटिव. So that's why we can cancel out these two squares on both sides without reversing the inequality. So this is the first one. Okay, mod of inner product of x y is less or equal to norm x norm y for all x y in x. Now second, we check this norm, it satisfies all the properties of norm, this function that we have defined. So also this what's this? It's by definition non-negative square root, so it's always greater or equal to 0 for all x belongs to x. Also this. And second, norm x is equal to 0 if and only if inner product of x with x, by definition it is equal to inner product equal to 0, and which is true if and only if inner product of x with x is 0, and by definition of the inner product of x with x is 0 if and only if x is equal to 0. So norm is 0 if and only if x equals 0. Third, the triangle inequality. Let's check that norm of x plus y, it should be less or equal to norm x plus norm y. Okay, so let's find out this. First let's take the square of this. This is by definition it is the inner product of x plus y with x plus y, because by definition what's norm of x plus y? Definition क्या है इसकी? It's equal to inner product of x plus y with x plus y, and it's non-negative square root. This is the definition of norm here. So I'm taking square on this side, so therefore yes. So norm of x plus y square is equal to inner product of x plus y with x plus y. Now we expand this. It's inner product of x with x plus inner product of x with y plus inner product of y with x plus inner product of y with y. Okay, so first one, this is again norm x square. This is equal to norm x square plus inner product of x with y plus its inner product of x with y, its conjugate. Okay, this plus inner product of y with y is the norm y whole square. That's equal to norm x whole square plus this it's a complex number plus its conjugate. It's like z plus z conjugate, so that's twice the real part of z. Z plus z conjugate, that's twice real part of the, like if z is x plus iota y, z conjugate will be x minus iota y, then their sum is will be 2x, which is a twice real part of the complex number. So it's twice real part of the complex number is the inner product xy plus norm y square. But always the real part is always less or equal to the mod of the complex number. This is less or equal to norm x square plus twice this number. This is a complex number. This is the real part of the complex number, and this is always less or equal to the mod of the complex number. Okay, plus norm y square. Now this you have done in the first part. This is less or equal to norm x norm y. It's again less or equal to norm x square plus twice norm x norm y plus norm y square. So that means we have this norm of x plus y whole square is less or equal to norm x plus norm y whole square, because it is a square plus 2ab plus b square. So we can cancel out these two squares because they are all non-negative numbers actually. So this means norm of x plus y is less or equal to norm x plus norm y. So that's your triangle inequality of norm. So now we prove the last one, last property. That's the fourth one, which for any scalar k, let's choose alpha in the scalar field k and x in the x, then norm of alpha x square. Okay, this is equal to inner product of alpha x with alpha x, that's equal to alpha conjugate and inner product of x with x, but alpha conjugate is mod alpha square, and this is norm x square. Now अब आप square को cancel कर सकते हो. This is norm alpha x is equal to mod alpha times norm x. So therefore this is a norm, is a norm on x. तो उसकी वो नॉर्म की सारी प्रॉपर्टीज है. इट्स अ नॉर्म ऑन एक्स. अब हम फर्स्ट पार्ट जो है वो हम प्रूव करेंगे. So first part, so we have assumed that xn minus x converges to 0, yn minus y converges to 0. So let norm of xn minus x, it converges to 0, and norm of yn minus y, it converges to 0. So this implies this sequence xn and y, they are bounded. This is a bounded, हमें इसकी ज़रूरत ज़्यादा है, is a bounded sequence, is a bounded sequence. So that means there exists some m positive such that norm of xn is less or equal to m for all n greater or equal to 1. हमें प्रूव करना है this inner product of x and yn is converges to inner product of xy. So let epsilon be any positive number. Choose any epsilon positive number. Now here this x and it converges to x, y it converges to y. So that means I can find. So I can choose a single n, capital N. I can choose a n1 for this sequence and n2 for this sequence. Then I choose the maximum of these two, n1 and n2, that will work for both the sequences. So let's choose that n here. Choose n greater or equal to 1 such that this norm of xn minus x, it's less than. I have to choose this epsilon appropriately so that finally I can find epsilon actually. How do I do that? So I should write here epsilon divided by twice m and norm of yn minus y, it's this thing by 2. Let's choose this as epsilon divided by twice norm y, okay, because epsilon divided by twice norm y is also a positive number. Okay, all right. So then for all n greater or equal to capital N, this is true for each n greater or equal to capital N. Now let's see this difference in the mod of the inner product of x and yn with x, y. Okay, we show that difference is less than epsilon. Now mod of जो आपको प्रूव करना है x and yn, यहाँ तक तो आपके पास एक गिवन था सारा xy. You will show that this difference is less than epsilon for all n greater or equal to capital N. So that will prove this converges to xy. Okay. So this is equal to inner product of xn with yn. Okay. Then I write here minus inner product of xn with y plus inner product of xn with y and minus inner product of x with y. Okay, this is it. So let's separate triangle inequality for these two. It's less or equal to mod of inner product of xn with yn minus inner product of xn with y plus mod of inner product of xn with y minus inner product of x with y. Okay. Now this is equal to, so these two are same here, x and xn, so it's inner product of xn with yn minus y plus mod of inner product. This y and y is again same here, it's xn minus x and the inner product of xn minus x with y. Okay, this one. Now you apply Shiva's inequality or the inequality that you have already proved in the first, which is less or equal to norm of xn and norm of yn minus y. plus this one, it's less or equal to norm of xn minus x, and then norm of y, and this is less or equal to m, so it's less or equal to capital M, and then norm of xn minus x plus norm of yn minus y, and norm y is it's okay. So this is, so it's norm of y, and here, okay, here it's xn minus x, this is yn minus y, this is xn minus x, okay. Now this is less than m times epsilon divided by twice m plus, and